All right. Well, it is just past 6 o'clock. I'd like to welcome you all and thank you for joining us here at the 2022 Fall Lecture Series through Rocky Mountain ACSM. I'm Tony Nunez, president of Rocky Mountain ACSM. I just want to remind everyone that we will take questions at the end of Dr. Grabowski's lecture, and we will pretty much say that you can put questions in the chat at any time, but just realize that we're not going to get to them until the end of the talk. Also, for those of you who are joining, please make sure to complete the survey that you'll receive after the webinar. That will come to your email that you registered for this talk through. And please make sure to do that for us so we can improve going forward. And finally, without further ado, I'd like to introduce Dr. Alena Grabowski. She's over at CU Boulder, and I will let her take it away as to what she wants you to know about herself.
Great, thank you. So I'm an associate professor at the University of Colorado Boulder, and I'm also a research healthcare scientist with the Department of Veterans Affairs. And today I'm going to talk to you about something that has been somewhat controversial over the years, which is the use of running specific prostheses for people with below the knee amputations. And I'm going to focus my efforts on all of the research that I've conducted on the use of running specific prostheses. The reason that they've become controversial is that the use of these prostheses by a few select athletes has enabled them to qualify for the Olympic Games. And the governing body of the Olympic Games has made rules and regulations regarding the use of prostheses. And I'll talk about those rules and the data that we've collected to try to address those rules. So for those that don't know, running specific prostheses are made of carbon fiber typically, and they attach to the residual limb of a person with an amputation through a rigid socket. So it's kind of this device that surrounds the residual limb. And typically prostheses are either attached behind the socket, like this example that I've got up, or they're attached underneath the prosthetic socket. And I'll show you an example of that in a little bit. To be clear, when we're comparing prostheses and biological limbs, prostheses are made of carbon fiber so they can store and return energy much like a spring, but they don't have a motor, they don't have an articulating joint. They simply can run forward and be spring-like, but they don't really mimic a biological limb that well. And so the use of them in sport is controversial, I think, in part because they look so different than a biological limb, and people have made assumptions about their use. And I want to be clear about the use of those prostheses and what they can and can't do. And in fact, about a little over a decade ago, the International Association of Athletics Federations, which is the governing body, or was the governing body of track and field, they've switched their name now to World Athletics. But they put forth a rule to govern the use of running specific prostheses. That rule basically bans the use of any technical device that incorporates springs, wheels, or any other element that provides a user with an advantage over another athlete not using such a device. So this rule really governs the use of springs, which is what running specific prostheses do. They act like springs. And there's a couple other key words in this rule. Basically, the IAAF at the time was burdened with showing whether an athlete has an advantage or a disadvantage over another athlete. And that's a really tricky thing to do in science and in a regulation. However, this was the rule put forth, and we have to try to start to think then about how we might suggest that an athlete has an advantage or a disadvantage due to the use of this device. So in order to compare prosthetic legs and biological legs, it's important, well, at least in my world, to study biomechanics or how we move. So again, forgive me if you already know all of these relationships, but I'm just going to kind of go through basic biomechanics for running and sprinting, because this rule is really governing running and sprinting. So in general, velocity equals stride frequency times stride length. And a stride is an event in one foot to the same event in the same foot. And that's the image I have displayed up here. So we've got a right heel strike and ground contact. That's what TC, it's the time of ground contact. Then an aerial phase when both legs are off the ground, or TA. And then another ground contact, another aerial time. And then finally you have a stride. So velocity basically is the number of strides you take per second times the length that you go forward during a stride. And so we can try to start to compare prosthetic and biological limbs by using this relationship. But for people with a unilateral amputation or bilateral amputations, it's really key to try to compare each individual leg and try to see how those legs differ. And so we can rearrange the velocity equation to try to understand some of the components that influence velocity. And we can do that by looking at things like the ground reaction force that a person applies onto the ground. And that looks something like this. This is a vertical force, and the units are in newtons across time. And we have a very characteristic way in which we apply force onto the ground when we run. And that's represented by this graph. And the amount of force you can generate on the ground directly governs your velocity. If you can apply more force during ground contact in the vertical direction, you can go faster. And we can rearrange the velocity equation to incorporate those forces by setting velocity equal to the stance average vertical force normalized to body weight. And that's basically the average force during ground contact. And that's multiplied by contact length, or the distance that you go forward when you have your foot on the ground. It's kind of looking at the center of mass distance, or you can think of it as your hip, how far forward your hip travels during ground contact, times the step frequency, or the number of steps you take per unit time, the steps per second. And a step is simply half a stride. So we can look at ground contact and aerial time for, let's say, a prosthetic leg, and compare that to a biological leg and get a sense of the differences between each of these different types of legs, and then really try to understand how the device works compared to a biological leg. So these are important relationships, and we've used these relationships in the past. And one of those athletes that we used these relationships on was a guy named Oscar Pistorius. This, fortunately or unfortunately, started the controversy about the use of running specific prostheses, because about 10 or so years ago, Oscar was running a 400-meter sprint, or once around the track, faster than the Olympic qualifying time. His personal record is 45.07 seconds, and he uses running specific prostheses. He has bilateral below the knee amputations. He's an athlete from South Africa. And his use of prostheses was contested based on the rule that I showed you just a little while ago. And so the IAAF commissioned a study on Oscar to try to understand how his prostheses affected his performance and whether they provided an advantage or not. And their results, which were publicized around the world, suggested that his prostheses provided him with an advantage, specifically a metabolic advantage, and specifically for the last 100 of a 400-meter sprint. However, the measurements that they used to get to that point to suggest that he had an advantage were fundamentally flawed. They tried to measure his aerobic metabolism during a simulated 400-meter sprint. And by doing that, they violated basically the gold standard for measuring aerobic metabolism, which is done at a submaximal intensity for at least 5 minutes so that we can get a steady state measure and compare that to other athletes. However, they used the last 100 of a 400-meter sprint, which is about maybe 12 seconds, and try to use that data, compared it to non-amputees, and suggested he had an unfair advantage. So when looking at those data and trying to understand what they were using to try to compare between prosthetic legs and biological legs, we disagreed with the findings. However, those findings were used to ban Oscar from competing. Oscar appealed that decision, and he partly appealed that decision through some research that I was able to take part in with a group of international scientists. We conducted a series of tests on Oscar, and we found actually that he had no difference in aerobic metabolism compared to non-amputee sprinters of a similar caliber. And we used gold standard measurements to do that, to make that finding. However, his use of running specific prostheses resulted in very different biomechanics compared to non-amputees. He had lower stance average vertical ground reaction forces, longer ground contact times, and faster step frequencies at his fastest speed. We collected these data, we presented them to the Court of Arbitration for Sport, and we successfully appealed the decision made by the IAAF. So Oscar was allowed to compete. And he did so in 2012. He ran the 400-meter sprint, he advanced to the semifinals, and he finished last in the semifinals. However, this seemed to be, in my mind, a huge step forward in understanding how prostheses and biological limbs compare. But there was a lot more research to be done because we didn't really have a fundamental understanding of the differences or similarities between these devices. And there were a lot of people that were questioning the use of these devices because they weren't familiar with what they could or could not do. In addition, during this time frame between when we appealed the decision by the IAAF and Oscar was allowed to compete, the IAAF changed the rule. Their rule now states that they ban the use of any mechanical aid unless the athlete can establish on the balance of probabilities that the use of an aid would not provide him with an overall competitive advantage over an athlete not using such an aid. This rule is complicated, but in general places the burden of proof on an athlete to show that they don't have an advantage. And so in some ways, it's suggesting that the athlete has to prove that they are not guilty. But that was the rule made in 2009, and it stood until about a year ago. And I'll tell you more about that story as we go. However, we were still really interested, despite this rule, in how prostheses compared to biological limbs. And so myself and others did a number of studies to try to understand these relationships. And one of those studies was using athletes with a unilateral below the knee amputation. These athletes are ideal because we can compare in the same athlete, same training, same age, same everything. We can compare a prosthetic leg to a biological leg. And we do that by having them run on an instrumented treadmill that measures the force that they can exert on the ground. And we can also measure their motion, which is the cameras that are in the background. And I'm going to run this video. Hopefully it will render okay on Zoom. But this is one of our fastest female athletes running at her maximum speed. And we wanted to characterize forces and biomechanics across a range of speeds up to maximum speed to really compare between the two legs of each individual athlete. So I'm going to run that video now. And then this is our fastest male athlete in the cohort that we measured. And what I hope you can appreciate from the video is how amazing these athletes are at using these spring devices. And so they're able to really control these devices at super fast speeds. And like I said before, we measured them at a range of speeds. So we started them at a jogging speed, measured their ground reaction forces, their motion, and then we went up all the way to their maximum speed, where maximum speed is having each athlete take at least 20 steps on the treadmill before they drift back. So to really get perspective on our results, I'm going to show you another video. And this is basically going to animate each of the athletes. You can see this athlete in the front has their running specific prosthesis, and then the rest of them is animated with a skeleton. And at the same time that the video is running, there'll be a scroll bar on the upper right that indicates the vertical force that's exerted on the ground in units of body weight over time. And so I'll start running that now. And the blue arrow is also indicative of the force that's exerted on the ground. And then we're going to slow it down so you can really get a sense of how the force is being exerted on the ground. And if you can kind of focus on both the video and the scroll bar, you can see that there's a distinct pattern in the ground reaction forces where you have a really high peak force and then a low peak force, where the high peak force corresponds with the unaffected leg, or UL, and the low peak force corresponds with the affected leg, or the prosthetic leg, or AL. And if we display this across this whole data collection, we have force in units of body weight versus time on that lower right graph for the unaffected and affected legs. And you can see that there's a big discrepancy between the forces. We actually found that across a range of speeds, there was a 9% higher unaffected leg stance average vertical ground reaction force compared to the affected leg. And because of this big difference between prosthetic and biological legs, this suggests that the use of running specific prostheses impair force generation, and that limits their maximum speed. So this is one component that's really important in performance, is how fast you can run, so your maximum speed. But in a 400-meter sprint, you're also regulated to use starting blocks. And so athletes with amputations use starting blocks, and they can choose whether they have their unaffected leg in the front block or the back block. And we conducted a study to try to understand whether it's better to have their unaffected leg in the front or back block. And in addition, we could really understand how prosthetic legs and biological legs compare between legs within the same athlete. So we had non-amputee athletes and athletes with a unilateral amputation complete maximum effort starts out of the starting blocks. We had them do their usual configuration, and then we switched their legs, but we kept the stance position the same between legs. So for example, athletes with amputations, if their unaffected leg was typically in the front block, we switched them and had their unaffected leg in the back block and asked them to do starts with that configuration. We actually found no difference between those two configurations, but when we can compare athletes with and without amputations, we can get a better perspective of how prostheses affect starting block performance. So here I've got a graph of the vertical force in units of body weight on the y-axis and horizontal force in units of body weight on the x-axis. And so to optimize your performance out of the starting blocks, you want to maximize horizontal force or horizontal velocity. So the angle that you are able to attain and the amount of force you can exert on the starting blocks influences that quickness out of the starting blocks. And so if we compare athletes with a unilateral amputation, which is the black dashed line, to non-amputees, basically non-amputees are 11% faster, or athletes with amputations are 11% slower due to the angle of the force that's being directed on the starting blocks. So we had force plates underneath each individual starting block in order to get these data. If we compare that to people that had just prosthetic limbs, and we did this by creatively looking at the forces that are exerted by the prosthetic leg in both configurations and combining those together, if we have a simulated athlete with bilateral amputations, they would be 23% slower than non-amputees. And so this again suggests that because running specific prostheses aren't able to generate the same amount of force as biological limbs, they impair force generation, and that limits acceleration out of the starting blocks. So far, two things are indicating that the use of prostheses, these springs, are not an advantage for athletes with amputations. In addition to starts and maximum speed, running around curves is important in a 400-meter sprint, where over half the race is run on a curve. And so we did an experiment where we had athletes with a unilateral amputation, both left and right leg amputations, run curves either in the counterclockwise direction, which is regulated by track and field. And we also had them run as fast as they could on the curve in the clockwise direction. And we compared that to their maximum speed on the straightaway. This gave us an indication of how having a prosthesis on the inside or outside of the lane relative to the inside of the curve affects curve running performance. So to put it another way, are athletes faster if they have a right leg amputation versus a left leg amputation? Because the prosthesis on the inside of the curve may limit their curve running performance more than having a prosthesis on the outside of the curve. And that is what we found. Athletes were 3.9% slower when they had their prosthesis on the inside of the curve versus the outside of the curve. Again, suggesting that running specific prostheses don't provide an advantage in maximum speed curve running performance. So lots of different studies that we've done to try to understand performance in sprinting. One other thing that we looked at was whether athletes had the appropriate prosthesis to be able to achieve fast sprint times. So we did a study where we looked at different prosthetic models, stiffnesses, and heights, and whether specific characteristics of the prosthesis would optimize performance. And here, when I say optimize, I mean go faster, have the fastest maximum speed. And so these series of studies were conducted by Dr. Owen Beck and Dr. Paula Taboga. What we had athletes do is that we had 5 athletes with bilateral below the knee amputations and 10 athletes with unilateral below the knee amputations use different prosthetic models. We had them use the Freedom Innovations Catapult prosthesis, the Autobach 1E90 Sprinter prosthesis, and the Oser Cheetah Extend prosthesis, where the Freedom Innovations prosthesis is C-shaped and it fits underneath the prosthetic socket. The Autobach is J-shaped and attaches behind the socket, and so is the Oser Cheetah Extend. We had each athlete try these 3 different prosthetic models, and we wanted to see, again, which one allowed them to go at a faster maximum speed. So they completed a series of studies where they started at a slow speed, they ran on a forced treadmill and went up all the way to their fastest maximum speed. And that basically was determining whether that was optimal, whether this model was optimal. In addition, within each model, we changed the stiffness of each prosthesis, where manufacturers recommend a certain stiffness of a prosthesis or certain resistance to compression for each athlete based on their mass and their activity level. So we used a recommended stiffness category by the prosthetic manufacturer, 1 category more stiff and 1 category less stiff in each of these 3 models. So now we've got 9 configurations. The best stiffness category within each of these prosthetic models was adjusted so that we went up 2 centimeters and down 2 centimeters in height, so that we could look at how height might affect maximum speed. We did this by using a customized height adjustment adapter on the J-shaped prostheses, or we changed the length of the pylon on the C-shaped prostheses. In all, each athlete used 15 different prosthetic configurations, and they were able to achieve their fast maximum speed with each of these different prosthetic configurations. To give you an idea of what that looked like, this is our fastest athlete at his fastest maximum speed using his optimal prosthesis, which he went on to use subsequently and then set a new Paralympic world record in the 200-meter sprint. But here is his fastest maximum speed. Let me make sure that the volume is turned down here. I'm not sure if you can hear it, but that's okay. And hopefully this renders well. So this particular athlete maxed out our treadmill speed. We've got a fast treadmill that measures forces, goes up to 30 miles an hour, and he hit 28 miles an hour. So exceptionally fast athlete. And what we found across all the athletes is that in athletes with bilateral amputations, they were 8 to 8.3% faster using J versus C-shaped prostheses. And athletes with unilateral amputations were also faster, 3.8 to 10.7% faster using J versus C-shaped prostheses. However, there was no significant effect of stiffness or height. And this is actually important later on. But what we found in general, over all these different studies then, if we compare prosthetic and biological legs, basically the use of prosthetic legs are slower, result in a slower maximum speed on a straightaway, slower starting block performance and acceleration out of the starting blocks, and slower maximum speed around curves. And the optimal running specific prosthesis is J-shaped, and there's no significant effect of stiffness or height. So that was a huge body of work that I just talked about, and it's really interesting to compare prosthetic and biological legs. However, there's still that rule that's made by the IAAF. And we started to really understand and try to comprehend that rule because of this athlete. So this is Blake Leeper. He's a US athlete with below the knee amputations, and his 400-meter personal record is actually faster than Oscar Pistorius. So his PR is 44.38 seconds, and that easily qualified for Tokyo in 2021. However, he had to abide by the rule that was put forth by the IAAF. And so in speaking with Blake and talking about the rule and what he needed to either show or not show, my crew took up his case pro bono and did research to try to understand his use of running specific prostheses compared to athletes that were not using such devices. So we compared him to the best non-amputee athletes. And we measured 5 performance metrics, 5 things that we think have a strong influence on 400-meter performance. Some of them I've already talked about. So 400-meter performance can be influenced by the start and acceleration out of the starting blocks. So we measured that. It can be influenced by biomechanics and maximum speed. So we measured and compared that. Also, curve running maximum velocity, we measured and compared. And aerobic metabolism, though it plays a component, it's difficult to assess how it influences 400-meter performance, but it does have some influence. So we measured that. And then we measured sprint endurance, and I'll talk about that. This is a nice metric, and it associates really well with 400-meter performance. And it also incorporates some element of measuring an athlete's ability to fatigue or not. So if we start with the starts and acceleration out of the starting blocks, we had Blake perform a series of starts where he had force plates positioned underneath each starting block to try to compare his horizontal acceleration out of the starting blocks compared to those of non-amputees. We also measured his time to 20 meters, and we compared that with elite level and sub-elite level non-amputees. And so if we look at his horizontal ground reaction forces and those of non-amputees, that's plotted on this graph. It's horizontal ground reaction force in units of body weight. Blake will always be in orange. BL is Blake Leaper. Non-amputees are in white, and that's NA. And you can see that there's a big and distinct difference between the amount of horizontal force that Blake exerts on the ground compared to non-amputees, such that he had a 30% slower acceleration out of the starting blocks. If we compare Blake's time to 20 meters, again, he's in orange and took 4.13 seconds, whereas elite and sub-elite non-amputees were almost a second faster than Blake Leaper. If we extend these data out to try to predict how fast he would run 100 in the first 100 of a 400-meter sprint compared to non-amputees, that would be about 1.4 seconds different compared to non-amputees. So it seems that the use of running specific prostheses that's been confirmed by other studies is a distinct disadvantage in the start and the acceleration phase. We also had him run at his maximum speed. We had him run at a range of speeds from 3 meters per second on up to his maximum speed. And we wanted to see if his maximum speed exceeded those values of non-amputees or of the athlete I just showed you. And so here's him at his maximum speed. The video starts at the fast speed and then slows down. And I want you to try it. If it renders okay, I want you to try and kind of focus on his use of prostheses and how he articulates that on this fast moving treadmill. All right, so Blake's maximum speed was fast, 11.4 meters per second, but it wasn't faster than the fastest athlete with the unilateral amputation, which was 11.5 meters per second. And it also wasn't as fast as non-amputee athletes, which was 11.7 meters per second. What does this tell us about the use of prostheses? Not much. It says he's not the fastest athlete in the world on a treadmill running at his maximum speed. However, he is exceptionally fast. His top speed is very fast, but we can't really draw a conclusion about advantage or disadvantage. We can only say that he has a very fast maximum speed. If we look at the biomechanics that underlie that fast speed, again, velocity is stance average vertical force times contact length times step frequency. If we look first at that stance average vertical ground reaction force in units of body weight, now I've got non-amputees in white, Blake Leaper in diamonds in orange, and Oscar Pistorius in blue diamonds across a range of velocities. If I hadn't delineated Blake's values from those of non-amputees, you probably wouldn't have noticed a difference. Yet Oscar's values are substantially lower, especially at those fast speeds. So it seems that somehow Blake is able to elicit the same or very similar stance average vertical grand reaction forces across a range of velocities and is not distinct from non-amputees. If we look at contact length, again, the same values and colors are associated with the same athletes. Once again, if I hadn't shown you Blake's values distinctly, you probably wouldn't be able to pick them out compared to non-amputees. And then finally, if I look at step frequency, again, we have the same thing. His values are not distinct from non-amputees, yet Oscar Pistorius had a much faster step frequency at the fast speeds. And we think that was to partially compensate for the low stance average vertical grand reaction forces that he had. However, if we compare Blake Leeper, we find that he has very similar biomechanics across a range of speed up to his maximum speed, which is really amazing. Honestly, all of the other studies that I've conducted have shown a dramatic difference in biomechanics, yet Blake is able to somehow utilize those prostheses in a way that allows him to achieve similar biomechanics compared to non-amputees. Okay, so next we measured his maximum speed on the straightaway and on curves, and we had him run on two different curve radii. We had him run on a 400 typical and regulation 400 meter curve radius for lane 1 of a 400 meter track. And then we also had him run on a typical radius for a 200 meter indoor track so that we could compare his values to some of the others that were in the literature. And there's also a model that predicts how much you're going to slow on a curve versus a straightaway. And so we compared his values to that model as well. And so what that model looks like is the white line here. So here I've got the curve running maximum velocity as a function of the straightaway maximum velocity, or as a ratio, where 1 is the straightaway. And then I've got curve radius on the bottom on the x-axis. And so basically a model proposed by Green in 1985 characterizes how much an athlete would be predicted to slow based on the curve radius and their maximum speed on the straightaway. And what we find basically is that both non-amputees and Blake Leeper slow on different curve radii, but Blake slows more than non-amputees. So if we compare lane 1 for an outdoor track, which is a 36.5 meter radius, and we compare that to straightaway running maximum velocity, non-amputees slow anywhere from 3 to 5%, so 3% based on Green, 5% based on a value in the literature, and Leeper slows by 6%. And we see that he slows more than the value that's reported in the literature at the shallower radius or at the smaller radius as well. So again, this suggests that if you're using a running specific prosthesis for curve running, you might have a disadvantage on the curve. And if we extrapolate the maximum curve running speed out to 100 meters, that would be about a 0.4 second difference. So again, suggesting that the use of running specific prostheses are not an advantage compared to biological limbs. We also measured Blake's aerobic metabolism by using gold standard measures. We had him run at his submaximal speed for 5 minutes. We took the average of the last 2 minutes, and we compared his running economy to those of others that are in the literature. We also did a VO2 max test with Blake and determined his aerobic capacity and compared those with others in the literature. And so what that looks like is here, we've got rate of oxygen consumption in milliliters of oxygen per kilogram per minute on the y-axis and velocity on the x-axis. And so at a given velocity, we can compare the economy or the rate of oxygen consumption across athletes. And what we find is that Blake has a better economy, 20 to 22% at the submaximal speeds. So this is the only instance that I can think of that might say, oh, maybe he's got a better aerobic metabolism. But aerobic metabolism is not only submaximal intensity, but also maximal intensity. So if we look at the VO2 max values and extrapolate the line for economy out to VO2 max, we actually find that Blake's values are 38% worse than those of non-amputees. And in fact, if we take that VO2 max value and put it down onto the x-axis, which is velocity at VO2 max, which is a way to kind of combine the two values of aerobic metabolism, economy and VO2 max, his values are 12% slower than those of non-amputees and of Oscar Pistorius, which is in blue. So what does this suggest about 400-meter performance? Well, he has worse aerobic metabolism as a whole compared to non-amputees, but we don't know directly how that affects 400-meter performance. Finally, we did another 400-meter performance metric test, which was something called sprint endurance. And I love this photo because this is the photo after that test. So what we ask athletes to do is basically run for as long as they can at a given fast speed on the treadmill. And that speed is really close to their top speed. And we try to have a speed where they can sustain that effort for anywhere from about 3 to 300 seconds. And that characterization of how long they can sustain that given fast speed gives us an idea of their fatigue or of their endurance. And so we did that. We've done that with both Oscar and Blake, and then a range of non-amputees. And when we compare values for those tests, we've got here velocity on the y-axis and the duration that each athlete can sustain that given velocity on the x-axis. We have non-amputees in white, Blake Leeper in orange, and Oscar in blue. And basically, there's an exponential decay, meaning that you can sustain a slower velocity for a longer period of time. And then there's an exponential relationship between those two things as you get to faster and faster maximum speeds. But to put this in perspective and compare it to all the values that are out in the literature, it's important to normalize these velocities to maximum speed. And so that's what we've done in the second graph. We have the velocity relative to the maximum velocity on the y-axis. And again, the duration the athlete can sustain that on the x-axis. And the predicted values are from many, many, many athletes who have conducted this test on the treadmill. And it characterizes the population really well. But the other thing that you can appreciate is that non-amputees, Oscar Pistorius and Blake Leeper, have almost exactly the same values and that same exponential decay as you go for a longer effort and a different given velocity relative to Vmax. So this suggests that there's no advantage to using running specific prostheses as far as having a longer or better endurance at a given maximum speed. So if I put all of these data together and we think about Blake Leeper compared to non-amputees and addressing that specific rule, we did so. We had 400-meter performance metrics. He was 23% slower in the start and acceleration phase. He had similar biomechanics and maximum velocity, 3% slower curve running maximum velocity, slower aerobic metabolism, and similar sprint endurance compared to non-amputees. So all of these data were provided to what's now called World Athletics, who governs the use of running specific prostheses, and they denied him the ability to compete. We took these data and presented them to the Court of Arbitration in Sport to appeal that decision, and we did so in summer of 2020. I was fortunately or unfortunately an expert witness within the case. I say unfortunately because it was a very stressful experience. However, I thought it was very important to present the data and try to understand how the use of running specific prostheses compared to non-amputees. And the CAS panel made two important decisions. The first is that the present rule, the IAAF rule, was stated as unlawful and invalid because it places the burden of proof on the athlete. So that rule has been overturned, and now the burden of proof is back onto World Athletics or IAAF. But the second ruling that they made was a bit of a surprise. The panel believed that increased leg length increases running speed, and thus Blake Leeper cannot use his prostheses to compete. So there's another rule that the Court of Arbitration in Sport cited in their ruling to try to figure out whether Blake Leeper should be allowed to compete using his current prostheses or not. And that rule basically governs how tall athletes with bilateral, below the knee or above the knee amputations can be based on their body segment dimensions and a rule called MASH. And MASH is a rule in the IPC, the International Paralympic Committee, that governs the height of athletes based on their maximum allowable standing height. And this maximum allowable standing height is calculated based on things like wingspan, ulnar length, femur length if people still have femurs, seated height, all sorts of different body dimensions go into a formula. However, that rule has changed probably about 5 times in the last decade, and they keep going taller and shorter for what doesn't seem to be any apparent reason. And the rule is a little bit challenging in that they try to govern the height of athletes with bilateral amputations using their running specific prostheses standing and compare it to standing barefoot height of non-amputees. So there's a couple important things though that were sort of neglected, I think, in this ruling. And one was that we didn't find that there was any difference in the height of an athlete based on their maximum speed. So if we change height, this is the results from that, its effects on maximum speed were not significant. So here I've got maximum speed on the y-axis, change in height in centimeters on the x-axis. IPC max is International Paralympic Committee, maximum allowable standing barefoot height. And basically what we did is in that study where we changed all the different prosthetic configurations, we also changed height. And we found that in athletes with bilateral amputations, there was no distinct difference in their maximum speed. And it didn't matter whether it was a difference in model or stiffness, but height had no effect, no significant effect on maximum speed. We had one athlete that basically had really long residual limb lengths, and that's why his changes in height were way out on the right of the scale. He started at 12 centimeters taller than IPC max, went up to 14, went down to 10 because he had C-shaped prostheses underneath his very long residual limbs. And likewise, there's one athlete that had shorter heights than IPC max, up to 6 centimeters or 5 centimeters shorter, because he had very short residual limbs and the build height of the prostheses were not tall enough. Needless to say, we considered all those things when we were doing our statistics, and we still found no difference in maximum speed based on changes in height, which makes it really confusing in this IPC rule that tries to regulate the height of athletes with bilateral amputations. And I think it's very unfair to this population because they're constantly having to change their height based on body segment dimensions and a population study that may not be based on them or based on anything that affects performance. In addition, when athletes run, they have differences between biological limbs and prosthetic limbs, right? So biological limbs can move, they can plantar flex and dorsiflex during running, and they do so by quite a bit. But prosthetic legs don't have that option. They're really dictated as far as they can compress and extend by the stiffness of the prosthesis. And so in running, prosthetic legs are actually relatively shorter than biological legs. And to achieve equivalent running leg lengths between athletes with and without amputations across speeds, we should actually be setting standing prosthetic legs to be almost 5% longer than standing biological legs. So the controversy rages on, and right now Blake is trying to retrain his body to be able to utilize prostheses that allow him to compete based on the maximum allowable standing height and the rule made by the IPC. And just a note, if we apply that rule made by the IPC to athletes, non-amputee athletes, and we use their body segment dimensions to predict their height, 20% of Olympic athletes would be excluded. So it's very challenging to have a couple different rules governing the use of running specific prostheses in sport. But hopefully today you've got a better perspective of how we've done research to try to understand these differences and how it's very challenging to show advantage, disadvantage, or abide by the rules made by World Athletics. With that, I'd like to thank you for your attention and thank my great graduate students and the athletes that have participated in the studies that we've conducted. Thank my funding sources and my collaborators. And I'd love to take any questions that you might have. I really appreciate your attention so far. Thank you.
Awesome. Thank you, Dr. Grabowski. That was great. It was very informative and a lot of information I didn't know regarding all the rules in this area. So we do have one question off the bat from Michelle. She said, when an athlete had to show that an athlete does not have an advantage over other athletes, a lot of athletes there, do they generally hire researchers, or are there other people who help them prove that they're not receiving an advantage?
Yeah, so far it's been this one athlete and this one researcher. So yeah, I knew Blake from some research that I'd conducted in the past. And so I actually contacted him to make him aware of the rule. He wasn't aware that the rule was the way that it was. And so I offered, I didn't think it was fair for him to pay me, or I thought that might be a conflict of interest. And so I really tried to take an approach where we made hypotheses ahead of time based on our data to try to understand how prostheses affect performance, and did it pro bono so that we didn't have to have him hire us or have there be any conflict of interest. So I think that's a really important point. And so far, I don't think that there are any other athletes that have tried to, well, that's not totally true. There's, so Marcus Ream is an athlete with a below the knee amputation who's an exceptional long jumper. And we did some research with him as well. That was also pro bono. And we didn't find a conclusive advantage disadvantage. We found a neutral result, but the IAAF didn't think that that satisfied their rule. And so they didn't allow him to compete at the Olympic level. And he didn't pursue it because he wasn't interested in going to the Court of Arbitration for Sport. So it's a small world in that capacity. There's not many athletes that are at that level to be able to try to even approach that rule.
Yeah, that makes sense. So I had a question based on some of the testing that you had to perform. The first being the sprint endurance test. Is that something that essentially replaces our Wingate test for non-amputee athletes?
Oh, that's a good question. And I wish I was more familiar. I should be more familiar with the Wingate test, but I'm not as familiar with the Wingate test. You busted me.
Sorry
no,
about that.
I'm teasing. Yeah, it's an approach that was put forth to try to understand 400 meter performance. And I think it actually does a good job of predicting that. But yeah, I would guess that it is probably similar in some respects to the Wingate test.
Yeah, because I would just assume that you're looking at anaerobic capacity with that 400 meter effort, right?
Right.
And that was kind of part two to my question. You'd mentioned that one of Oscar Pistorius's tests was aerobic, an aerobic test based on aerobic metabolism, which is pretty interesting based on the fact that a 400 meter is very highly anaerobic. So
Right.
I just wondering what your thoughts were on that.
Yeah, to my knowledge, there's no gold standard way to measure anaerobic metabolism in an athlete as they're performing. And so we can estimate the contribution of aerobic metabolism. And then, yeah, we can also use that sprint endurance test to try to estimate that component. But like I said, to my knowledge, there's nothing that accurately does that. So we can at least use aerobic metabolism as one point, and then estimate that if all athletes use about the same amount of anaerobic metabolism, then we can try to use aerobic metabolism at least as a proxy. But you're right, it's and I said it too, like we can use it, we can compare, but it really doesn't have a strong meaning because we don't know how much it affects 400 meter performance.
Gotcha. All right, we got another one here. What is your next focus for your research relating to this topic?
Ooh, that's a good question. Well, right now we're finishing up a project looking at whether we should have women specific running prostheses. And so I think that's kind of interesting and kind of a little different than this focus, but also trying to see if there's manipulations to running prostheses that we can make and seeing how those affect performance. I've also got a lot of interest in understanding how people with above the knee amputations use prostheses and if there are optimal recommendations for those. But I don't have anything top of mind yet that I'm going after with this particular population of athletes. Although I think there's a lot of room in understanding different types of devices and how maybe someday we can get to the place where we have a device that outperforms biological limbs. But unfortunately, I think we're still a long ways away from that.
Absolutely. Would the weight of a prosthesis play a role in stride length or stride frequency, and has this been examined?
Yeah, we did add small amounts of mass onto the prostheses when we did the study with unilateral amputees, and we tried to see if that had any sort of effect on their maximum speed, because adding a little bit of weight on the prosthesis might help a little bit more with symmetry for these athletes. Or another way to think about it is the inertia during the swing phase. It sometimes feels better for them. We didn't find that it had an effect on maximum speed. I don't know if we went to the detail of looking at stride length, stride frequency, but I would assume that by adding weight, you're going to decrease stride frequency. And then at the same speed, of course, you need to increase stride length. So there's always that trade-off between the two. And that's something that unfortunately got neglected in some of the arguments within the Court of Arbitration for Sport. They were trying to argue that if you had taller limbs, you would have longer stride lengths, and then you just get that for free. You wouldn't have any impact on stride frequency. So it's interesting to think about, and was very difficult to listen to, and I couldn't really interject. But you can't just get it all for free. Even if you have lighter prostheses, there's always going to be some other compensation that's happening. And sometimes you forget that. You assume everybody's Usain Bolt, they can go fast because they're super tall. But that wasn't the assumption when he first came on the scene. So yeah, it's interesting.
Goldilocks, right? It's,
Yeah.
too long, just right. Yeah, you would assume that. Just
Mhm.
looking at sprinters, there seems to be a relatively average height for your elite level sprinters, and Usain Bolt just happens to break that open.
Right. Yeah. But I do remember when he first started sprinting, people were like, oh, there's no way he's going to do well because he's just too tall. He's bigger than everybody else. It doesn't make sense. And then he started just kind of, obliterating everyone, which was great. But then now the argument is it's just different because anecdotally that's what's going on. But there's sort of, you're neglecting what the athlete's doing to train and to be able to perform at that level. So.
Absolutely. All right. I'm not seeing anything else in the chat right now. I kind of had something come into my mind. I know that they've been working on the physiological integration between the human nervous system and the prostheses. Have you seen anything growing on that, or anything in the field that you can talk to?
Yeah, for sprinting, it's very complicated, I think. But there has been some research, especially on lower limb prostheses, to try to use signals from the person to be able to drive the prostheses. So I'd say half my research is on running prostheses. The other half is really on other devices, such as devices used for walking. And we've been doing a lot of research on the use of a stance-based power prosthesis for walking. And there's more research that's being done to try to integrate either muscle activity as a control signal, or even nerve activity as control signals to try to drive those types of prostheses. But yeah, we're getting there, but it's a slow, steady race, I guess, to get there and to really use the person to be able to control the device.
Yeah, seems way beyond what I could ever imagine, honestly. Great. All right. Well, I'm not seeing anything else popping up in the chat. So let's just go ahead and let you call it early here. And thank you for a great talk. And thank you to all the attendees who showed up, and make sure to fill out that survey. And from all of us at Rocky Mountain ACSM, Dr. Grabowski, thank you so much and have a great night.
Thank you. You too.
Thanks.
Bye.
Bye now.